In this video, we're actually going to talk about some of the other things we can do with growth curve models involving residual covariance and heterogeneous variance. But before we do that, we need to talk about a brief history lesson. And that is about the nlme package, which is actually a predecessor to the LME4 package that dates all the way back to R's original predecessor, S. Both packages are written by many of the same authors. The reason we use LME4 is that it has several advantages over nlme. The most important are that it's faster, having been built on better linear algebra methods. It has extensions for the degrees of freedom adjustments. It can handle generalized linear models, and it's easier to write packages on top of. So there's a lot of reasons that LME4 is a better choice than an LME. It's also just more ubiquitous and more common. So we figured it would be better to teach LME4 than NLME because you're more likely to see it when you're looking at other people's code. However, there are a couple of features in NLME that are not available in LME4. These typically have to do with specifying complex covariance structures that aren't specifically nested or crossed. And this includes the ability to specify heterogeneous variances or correlated residuals. So this is important in growth curve modeling, as we will talk about in a moment. But first, we're going to go over the NLME syntax and how it differs from LME4. So it's pretty similar. The main difference is that instead of the Elmer function, we have the LME function. And instead of fitting our mixed effects, our random effects with the parentheses syntax inside the formula, we actually have a different argument that comes outside of the formula, where we specify random and then tilde random slopes and random intercepts, or the grouping variable, that is. So we see the outputs are very similar. One thing you note in NLME, you get the full degrees of freedom that you would get in a normal t-test. Ignore this. This is not the correct degrees of freedom. These are not adjusted. So don't read the degrees of freedom or p-value. There isn't a way to get the adjusted degrees of freedom that I'm aware of in NLME. So we just have to treat this t-value as a z-test, and you can see the t is pretty much the same as what you get from LME4, as well as the estimates and standard errors. And we see again the random effects are pretty similar. There isn't a way to call the random effects as a data frame as we do sometimes in LME4, but it does automatically print out both the variance and standard deviation, so we don't really need it. And we see that everything matches up here. We get the same outputs. So why is this important? Why are we learning NLME? So there's sort of another special feature that you talked about a little bit in lecture, both last week and this week in longitudinal analysis, and that's that the time variable is explicitly specifying measurement occasions, which raises some interesting possibilities. So unlike other level 1 variables, when we have a time variable, we may have reason to believe that there's a relationship in the errors across measurement occasions, and this may not be fully accounted for by the linear or nonlinear effect of time in our model. When the measurement intervals are equal, we can actually model this relationship using HLM, and we can use NLME to do this. And there are a few different options for this, and we're going to look at one example, which is autoregressive residual covariance with lag 1. So autoregressive residual covariance with lag 1, aka AR1, essentially, the idea is that as time passes, the error correlation between each successive time point is going to get increasingly small. So we expect time 1 to look more like time 2 than we expect time 1 to look like time 4. So we expect the correlation across time points to gradually decrease. We can parameterize this in the AR1, autoregressive lag 1 framework, using a correlation between two time points, which is rho, typically rho, is the Greek letter you'll see parameterizing this. And then in AR1, we raise rho to the t power, where t is the number of time points apart the observations are, or the elements of the covariance matrix are. So when time points are only 1 point apart, like time 1 and time 2, t is 1. Then if you compare time 1 to time 3, t would get raised to 2. Time 1 to time 4, t would get raised to 3, so on and so forth. And since rho is bounded by -1 and 1, since it's a correlation, increasing the exponent will decrease this rho parameter, and that will decrease the residual covariance. So in nlme, we can specify the residual covariance using the core argument and specifying core equals core AR1, and then you specify the form, and you just specify one grouped by ID. And so here, using the same example data that we looked at last week, we can specify it like this. Note that we also have to include the NA action because nlme isn't as smart about handling missing data as LME4. And then we check the correlation structure portion of the summary output. It actually uses phi instead of rho, and it's unfortunately going to be cut off on the next slide. You can look at the slides or the video that we looked at when we recorded the Zoom session if you want to see. But the rho value, it calls it phi. It's right below this. It's just unfortunately I can't capture it in this particular slide. It is on the PDF version of the slide, but not the HTML version. So finally, there's one other consideration that we can think about, which is the heterogeneity of variance. And this is a common assumption across many statistical models that we may want to specifically reconsider when we have longitudinal designs. So one of the reasons is we may think that time causes variance to change. So the variances over time might be different. So an example might be if you repeatedly measure math scores of students over a school year, do we expect the variance in math scores to be equal at all occasions? And ideally, they won't be. Ideally, these variances will hopefully converge as the students learn the math material. So we can specify this using this weights equal var ident form equals tilde1 vertical bar time in LME. And so the different variances can then be found in the variance portion of the function. So here I fit the model, and so again, it's cut off. It's down here below the variance function, but this is how you would fit it. We can check for additional types of residual covariance arguments using by looking at the core classes vignette, which can be called in our